So now we're going to talk about combustion of fuels. So combustion. As crude oil is mostly a mixture of alkanes, its combustion therefore follows a typical pattern of alkanes. In the presence of sufficient oxygen, carbon dioxide and water are produced. For example, let's do hexadecane, which is C16H34. It burns according to, there's two C1634s plus 49 O2s goes to 32 carbon dioxide gas plus 34 H2O liquid. So other products of combustion include sulfur dioxide, nitrogen oxides, carbon monoxide, and particulate carbon, which is soot. The latter two are produced in situations where insufficient oxygen is present. Soot is often seen as black smoke under conditions of heavy acceleration or when engines are poorly tuned. The following equations illustrate how less oxygen is required to make particulate soot. So in this case, let's go back to our old friend hexadecane. So far less oxygen molecules, 32 carbon plus 34 water molecules. So liquid. In the past decade, however, considerable advances in both engine technology and fuel quality have led to a significant reduction in all of these emissions. Two such examples are the introduction of ultra low sulfur diesel which not only lowers emissions from sulfur dioxide but also allows for more sophisticated pollution control measures in engines itself, and the introduction of computer-controlled self-cleaning exhaust filters designed to remove soot. Our main concern is energy and extracting it from fuels by combustion. A useful quantity in this context is the heat of combustion, or more precisely, the molar heat of combustion. So the molar. The molar heat of combustion of a substance is the heat liberated when 1 mole of the substance undergoes complete combustion, combustion being with oxygen at standard atmospheric pressures, with final products being carbon dioxide gas and liquid water. Combustion, or burning, is always exothermic. This means that heat is always given out, so delta H for combustion process is always negative. This difference in sign, using a positive value for heat of combustion, while the enthalpy change of the reaction is negative, can be a trap when working problems. Remember that combustion reactions are always exothermic, and this helps to avoid any confusion. Enthalpy change for combustion is sometimes abbreviated to the enthalpy of combustion. Sometimes the molar heat of combustion is just called heat of combustion. The per mole in the units makes it clear that it's molar heat. Okay, so how do we calculate out the heat of combustion? Okay, heat of combustion is equal to delta Hc. For burning of fuels, and let's just call it combustion of fuels. Remember, we need to set whatever fuel we're burning to 1 mole, and then balance the equation to that. Okay, so in this case, we have 1 mole of ethane. We're going to need 3.5 moles of oxygen gas plus 2 moles of carbon dioxide and 3 moles of water formed. Okay, and let's just make sure it's balanced out. 2 carbons on the reactant side, 2 carbons on the product side, 7 oxygens on the reactant side, 7 oxygens on the product side, 6 hydrogens All right, so I've cleaned it up a little bit. So let's calculate the heat of combustion of ethane. So let's do heat of combustion of ethane. Okay, so usually it's written like this, delta H C, and then parentheses, C2, you know, you put your fuel in there, whatever is combusting, but let's just go ahead and write delta HC, okay? So it's important to note that delta HC is going to be the total, so let's put the total sum, and that's usually dictated, usually looks like that, so sigma delta heat of formations for the products minus the total sum. I'm actually going to put this, the heat of formation of the reactants. Okay, so let's go on from there. Let's go ahead and see how this would be done. Delta H of C, or sub C as it's sometimes called, 2 times the heat of formation carbon dioxide. Remember, it's the products plus 3 times that the heat of formation of water minus, I'm going to put 1 so that we can be clear on it, 1 times, because it's 1 molar equivalent, heat of formation of ethane, plus it's going to be 3.5 times the heat of formation of oxygen. Okay. So let's go ahead and do it further. So let's assume that given that delta heat of formation of ethane gas, CO2, and H2O are negative 84.7 kilojoules per mole. That's my funny notation again there, times per mole. Negative 393.5 kilojoules per mole, and minus 285.8 kilojoules per mole. So that's kind of scrambled around in there, but we get the idea. Okay, so delta H sub C, let's put in the values right here. So it'll be 2 times carbon dioxide, so minus 393.5 kg per mole. I'll just put per mole, do it the normal way, plus 3 times 285.8 kilojoules per mole minus, it'll be minus 84 minus 84.7 kilojoules per mole, and then plus, it's going to be plus the heat of formation for oxygen. And when we're talking about oxygen, all elements in their standard states, such as oxygen gas, solid carbon, in the form of like diamond have a standard enthalpy of formation of 0, and there is no change involved in the formation. They just spontaneously become it. So there's no heat of formation. So it's going to be 0. Okay. So let's go ahead and do this further. So delta H sub C is equal to minus 787 kilojoules per mole plus minus 800. Of course, it's gonna, it's gonna be a minus, but let's do it right. Kilojoules per mole. Subtract this from minus 84.7 kilojoules per mole, which is then going to, then it equals, let's take it further down. I always like to show my steps for this reason, because I make mistakes. 0.4 kilojoules per mole plus 84.7 kilojoules per mole is going to equal minus 1,579.7 kilojoules per mole. So in reality, we can kind of think of it like this. We can always think of it as the fuel plus some amount of oxygen when it's set to 1 molar equivalent of the fuel going to carbon dioxide plus water. And remembering that the heat of formation of oxygen is 0. Here are some other values for molar heat to combustion for some common substances. All right. I'll see you later.